Chapter 4 deepens our understanding of thermodynamics by opening up the question of entropy. And entropy stands as one of the most fascinating concepts in thermodynamics. And the word entropy conjures up many notions of the esoteric nature of the sciences. But as we'll see, entropy controls a vast range of processes that we observe every day. And energy and entropy in combination determine how a process operates spontaneously, that is, without the intervention of human influence. Nature is driven by spontaneous processes that are controlled equally by energy and entropy. So while energy is far more common in this discussion, entropy turns out to be extremely important for understanding these spontaneous processes. An important example of how entropy controls extremely important aspects of both energy and, in fact, climate is methane clathrates. Clathrates were discovered by Michael Faraday, and they turn out to be very important thermodynamically because if we start with the structure of water, we can describe this as a cage constructed of H2O with its hydrogen bonding structure. But a clathrate involves the inclusion of a methane molecule inside that framework of water. And on the face of it, this is remarkable. How can methane find its way into the structure of water? In fact, this diagram is a diagram of methane clathrate taken off the floor of the ocean off the west coast, and a lighter was touched to it and it bursts into flame. And it bursts into flame because the methane is reacting with oxygen to produce CO2 and water, and that ice actually burns. Well, it turns out that entropy is directly related to this because entropy, it turns out, is a measure of the degree of disorganization of structures. And when you look at methane trapped inside a water matrix, that looks like it's highly organized. But it turns out that nature abhors a vacuum. It wants to insert molecules wherever it can into a system. And nature inserts methane, primarily from the anaerobic decomposition of organic material, into that structure of ice because it wants to fill the void or the vacuum left by the space within that hydrogen bonded structure. So methane enters into this structure. But let's take a look at how vast these stores of energy are in a methane clathrate. One of the most revealing aspects is to compare the chemical energy contained in all known clathrates to the total amount of energy contained in all of the Earth's oil, that is petroleum, natural gas, and coal deposits. On the face of it, you would think, well, there's vastly more energy contained in petroleum, natural gas, and coal deposits than there could ever be in methane clathrates. But in fact, the reverse is true. Approximately 3 times as much chemical energy is contained in methane clathrates globally than in all known reservoirs of petroleum, natural gas, and coal. And the degree to which these methane clathrates are ubiquitous is one of the remarkable stories evolving out of an understanding of how entropy actually controls in a very important way the structure and function of molecules globally. But methane clathrates, along with entropy, carry another important message, and that is the containment of methane in these methane clathrates, and in fact the containment of reactive carbon in permafrost, turns out to be one of the most important feedbacks in the climate system because, as we saw before, the Arctic is melting down very rapidly. It's losing its permanent ice. So let's compare the release of methane and CO2 from these clathrates and permafrost with the carbon added to the atmosphere through the extraction, distribution, and combustion of fossil fuels. So in this diagram, the vertical axis measures the carbon dioxide emissions measured in gigatons of carbon per year. That's gigatons of carbon contained in CO2 per year. And we can plot that against calendar time from 1990 up to 2015. And we have global measurements of how much carbon is added each year to the atmosphere through the combustion of fossil fuels. The Intergovernmental Panel on Climate Change lays out different scenarios each time they publish their results, and we can compare those scenarios with what was actually added. And one very important point here is that we've added more carbon to the atmosphere than the highest level of projected carbon release by the IPCC panel that does the analysis every few years. So we're releasing CO2 and methane into the atmosphere faster than the fastest profile that was forecast. But here's the remarkable thing. When we come back to the way entropy controls the formation of methane clathrates, and we look at what happens to the melting structure of the Arctic, if we take just the upper 3 meters of clathrate and permafrost, and we release just 0.5% of the reservoir of methane and CO2 from that upper 3 meters just in northern Alaska and Siberia, that 0.5% release equals all the carbon added to the atmosphere by all fossil fuel combustion globally. And so this feedback of the melting Arctic releasing additional CO2 and methane into the atmosphere turns out to be a central concern in climate studies. And it's all a question of how entropy controls the structure of these materials. So let's review very quickly again the lessons from these clathrates, the inclusion of methane into the water structure. And what this does is that it raises the melting point of the methane clathrates to 18 degrees C from what's of course 0 C for pure ice or pure frozen water. And so the methane clathrate does a number of things, including the stabilization of these clathrates. And this is, on the face of it, very fortunate, but it also contributes dramatically to the amount of methane contained in these systems because they're very stable on the ocean floor, where the control of the amount of clathrates depends not just on temperature but also on pressure.